Good day, everybody in physics land. Welcome to level 3. Can you believe you've made it this far? It's amazing. So, this is the Check Your Understanding 3.1 Forces, Definitions, and Equations. So, again, our skill for this unit is that I can define force, acceleration, mass, create free body diagrams of an object at rest at a constant velocity and accelerating to solve for a given variable with F equals ma. F being the force, and that is measured in newtons, and that is going to be equal to m, which is mass, and that's going to be measured in kilograms. And we have acceleration, which is measured in meters per second squared. Cool. A force. A force, I think I can make this to where it like as a special thing. That's too high. All right, force. A force is a push or pull upon an object resulting in the object's interaction with another object. Whenever there is an interaction between two objects, there is a force upon each of the objects. When the interaction ceases or stops, the two objects no longer experience the force. Forces only exist as a result of an interaction. So if we have no interaction, we have no forces. We're taking a look at two main types of forces. We have contact forces, so this would be like a push or pull, or forces resulting from action at a distance. And we're going to go into this a little bit later, but these have to do with fields, like gravitational fields, magnetic field, electric fields, and things like that, where there's no actual, doesn't look like anything's being in contact with the forces that are happening. Contact forces that we were going to be talking about are going to be like frictional forces, tension forces. So a tension would be like my pig hanging from the top of my flying pig. Oink, oink, oink. Oh my gosh, am I drawing an amazing pig? I think so. With wings. So my piggy that flies around, there's something holding that piggy up, and that is the force of tension. You can write that with a big T. Forces, normal forces. So anything sitting on a surface is a normal force. So right now my computer is on a table. If I have a box on a table, we'll see that we have a normal force going up. We have a gravitational force going down, but that's not a contact force. Air resistance is a force, and any type of push or pull is a force. Action at a distance, that we said earlier, are things that happen in fields. So like even though the sun and the planets exert gravitational pull on each other, they have a large spatial separation, so they're not in contact with each other. Forces, as we said earlier, are measured in newtons. Notice it is a capital N. It is not a lowercase n. Get those lowercase n's out of there. Pay attention to details. Oh, wow, I said it right here as well. Not that n. A force can be calculated from an object's mass multiplied by its acceleration. Here's the equation. You'll see it over and over again. And most of the time, actually, we'll see that an acceleration is a sum of all forces divided by the mass. And we'll use this equation a lot too. It's a little bit easier to see that if I increase the force and the mass stays the same, the acceleration increases. Or if I increase the mass and the force stays the same, the acceleration would decrease. So acceleration and force are directly proportional. While mass and acceleration are inversely proportional. Right? Like if you were sitting on a chair and I pushed you with a force, you would accelerate. Now let's say you and your friend were sitting on that same chair. If the mass went up and I kept the force the same, the acceleration would go down. It would be harder to push you guys because you'd have more mass. Notice force is in newtons, but only when we have a mass in kilograms an acceleration in meters per second squared. So for the rest of this year, we're going to be trying to keep all of our units in kilograms, not grams, meters, not centimeters or kilometers, and this will, oh, and seconds, of course. This will help us throughout the year, especially as we get into joules and volts, which also need things in kilograms and meters and seconds. Force is a vector, and that's why we had that huge vector drawing on the door, because it is a vector. And if you remember from that awesome movie, Despicable Me, Vector, I think he fights crime. Maybe no, he commits crime using both magnitude and direction. Oh yeah. So we need magnitude and direction, just like velocity, but this time we're really going to be using like plus or minus values or directions with these arrows. So I have an example here of a box sitting on a table, and I know that it is in the gravitational field. So I'm going to make one arrow down, and I'm going to call that, I can make a straight line. I'm going to call that the force of gravity. But notice it's not accelerating straight through the table. So there has to be another force there, and it's going to be opposite and equal to Fg, and that is going to be the normal force, Fn. And that's the same thing that I have here and here. I just wanted to show you how the thinking goes with that. So the normal force is anything sitting on a surface. Equilibrium. If the forces are in equilibrium and in opposite directions, then there is no net force. This is shown on the box on the table. If a gravitational force was 10 newtons and the normal force is 10 newtons, then the sum of all forces would be 10 newtons minus 10 newtons, which is 0 newtons. This is also shown by the Greek letter sigma, right? So if this was equal to 10 newtons, and this was equal to 10 newtons, then the sum of all forces are going to be equal. The sum of all forces are going to be 0, right? The sum of all forces are equal to 0. So it is not accelerating. Therefore, no acceleration. However, let's say I had a box sitting on a surface. Oh, that is ugly. Let me get my surface first. All right, and then let's say I have a box here. And let's say Mr. Madden is pushing it with a force of 30 newtons. But then there is a frictional force of 10 newtons. Okay, so now in this situation, the sum of all forces are not equal to 0. Therefore, the sum of all forces are going to be equal to mass times acceleration. And we could figure out the acceleration because that would just be the sum of all forces divided by the mass. So I could figure out how fast this box is accelerating with those forces being applied to it. So again, this is the Greek letter sigma. It means sum of all forces. Here again, if the sum of all forces equals 0, then acceleration equals 0. Now acceleration, oh my goodness, we know acceleration. You guys have done acceleration. You love acceleration. I know it. Come on, admit it. We've already done that. So you know what acceleration is. You know that it has the units of meters per second squared. Mass, remember, we're going to keep that in kilograms, and that means forces are going to be in newtons. Those are going to be the units. Oh my goodness, this is the example I just said above. Cool. Well, here it is again. Let's say, the box is 5 kilograms. So again, this is how you're going to solve these problems. SOLVE. You're going to write down what you know. Okay, well, I know that the sum of all forces from 30, this is in the opposite direction, so it's going to be 30 minus 10, is going to be equal to 20. So I know the sum of all forces is equal to 20, right? And that's what's right here, 20 newtons. The mass is 5 kilograms. I'm looking for my acceleration. So here's how I solve. If I have sum of all forces equal to mass times acceleration, I solve for acceleration. And then I get the sum of all forces divided by the mass is equal to the acceleration. Well, that's 20 newtons divided by 5 kilograms. That gives me 4 meters per second squared. Notice, this is the equation that I've shown right here and there. I've shown my work right here. And I've shown my correct answer with units right here. That would be perfectly done. Cool. Yeah, Mr. Madden, that's cool. We're going to do this together in class, but I thought I would give you guys a little preview so you can practice. So let's take a look at Mass 1. Use or let's go to number 1. Use physics words to describe the motion of the modified Atwood's machine. So this is a type of physics setup that we use to look at acceleration and masses and the relationship. So what it is I have a cart on a table, and then it has this string that goes over a pulley and then goes down to another mass. So this mass is going to be at a constant acceleration from gravity, and it is going to pull. It's going to have a tension force here, which pulls this cart because it also has a tension force here, and that cart is pulled and accelerates at the same acceleration of this second mass. So I'm going to say, use physics words to describe the motion of the modified Atwood's machine. The modified Atwood's, and he's a man, so that's actually capitalized, Atwood's machine will accelerate. Good. Number 2, draw a free body diagram for each of the masses on the black dots above. Okay, let's start with mass 1, and let's ask ourselves, I don't know if there's any friction. Are we going to do any friction? Let's say no friction. No friction. So we'll do no friction in red. Maybe I'll add a little bit of friction in and do that in a different color. So is gravity acting on mass 1? Well, it's on Earth. So yeah, definitely it will have gravity. So I have a force of gravity. Is it accelerating straight down or straight up? No. That means it has to be some other force besides the force of gravity. Well, that's going to be the normal force. And I make sure that that arrow is equal and opposite to the one that I drew below, because the sum of all forces in the y direction must be 0, because it's not accelerating up off the table, it's not accelerating down through the table. And what's causing it to accelerate? Well, there's a tension force here that's causing it to accelerate, and I will put that, I will put that right here. Notice how all my lines for my free body diagram come from one dot. And I have all of them labeled force of tension. Okay, let's take a look at mass number 2. Well, mass number 2 is hanging there. I'm going to call this force of gravity on mass 1 over here. So it's on Earth, so there's definitely gravity. And then I'm going to put an arrow here, and I'm going to call that the force of gravity on mass 2. And it is accelerating down, but there's a force of tension going up. And this force of tension is the exact same as this force of tension, because they are on the same string. Okay, free body diagram is done. If there was friction, we would show friction between the wheels of the cart here. We would show that as an arrow this way, where I would call this the force of friction. But we're going to pretend there's no friction in this situation. Okay, so I have drawn a free body diagram. Now, draw an arrow that follows the path and points in the direction of the acceleration. So let's see, it would go like this and then down. Okay, next to that arrow, draw an A+ with a circle around it to remind us which direction is positive. We're going to want to say that the direction that it's accelerating is positive. And it's kind of weird, but I'm going to make this my X direction, where I start here and go around this corner and down. I'm going to call all of that my X direction. Next to the arrow, draw an arrow plus circle around. Do the sum of all forces equal to 0? No, right? Because it's accelerating. No. The system is accelerating. It's going to accelerate to the right and down. If not, what does sum of all forces equal to? Okay, let's take a look here. Well, the sum of all forces in the y direction, oh, you know what? The sum of all forces in the y direction are equal to 0, because this FGM right here and this force normal are actually this equal and opposite. So in the y direction, it does cancel out. Maybe I modify that here. Yes. Yes, in the y direction. No, in the x direction. Okay. Well, sum of all forces are equal to 0 in the y direction, but that leaves us these forces in the x direction. So the forces in my x direction, I have the force of tension, I have the force of tension, and I have the FGM2. So those are my forces in the y direction. Let me make that a little bit more clear. So in my x direction, force of tension, and force of gravity on the mass number 2. So let's take a look at what all those equal when I put them together. Well, the sum of all forces in the x direction are going to be, let's see, what's positive? Ooh, look, we said anything going in this direction is going to be positive. So that means FGM2 is positive. So sum of all forces is equal to FG mass number 2, but this FT right here is in the negative direction because its arrow is pointing in the opposite direction of what we said was positive. That's going to be minus FT. And then I have this force right here, which is in the positive direction. So then that becomes plus FT. Well, an FT minus an FT is 0. So that means these cancel out. The sum of all forces in my x direction are going to be equal to Fg mass 2, right? And if I look at this, the only thing that's going to cause the acceleration of this system is going to be mass 2. The rest of the system is not going to cause an acceleration. So the sum of all forces are going to be equal to FGM2, and that's it. So let's take all those, which is just 1. I'm going to say FGM2 is equal to the mass of the system times acceleration. What is the mass of the entire system? Well, the mass of the system is going to be equal to the things that are accelerating. Well, that's going to be M1 plus M2. Okay, so if I have FG M2 is equal to mass 1 plus mass 2 times acceleration, how can I solve for acceleration? Well, I need to get acceleration by itself, so I'm going to divide both sides by M1 plus M2. And these cancel out over here. So my final answer that I get is acceleration is equal to FGM2 divided by mass 1 plus mass 2. Okay, cool. Conceptual questions. When will the acceleration be closest to 0 meters per second? When will this acceleration be closest to 0 meters per second? Well, if this M2 is what's causing the acceleration, then if this force, if FGM2 is small and M1 is large, it's going to accelerate very, very slowly. Could the acceleration be equal to 0 meters per second squared? Well, not if we didn't have any friction, right? If there was some friction, then the sum of all forces could equal 0 and we would not accelerate, right? Because in that case, if there was a force of friction, then my sum of all forces, let's do this in blue. If there was friction, then the sum of all forces would be equal to FGM2 minus FT plus FT minus F force of friction. These cancel out. My sum of all forces then, if I had friction, would be FGM2 minus the force of friction. Well, if these two are equal, and they're the only forces causing the acceleration, and they are equal and opposite, then the sum of all forces in the x direction would be 0, could be 0. So only if the sum of all forces in the x direction was equal to 0 could there be a constant velocity. Well, actually, if the sum of all forces were equal to 0, it could be put in motion and then have a constant velocity. And that is a little bit tricky. We're going to see that live in class of how that works. But we could also have the sum of all forces equal 0. And if that was the case, then theoretically, we could have a constant velocity, because all this means is no acceleration. And if I have a constant velocity, well, that also means no acceleration. So that could happen. What two situations could this be in equilibrium? Well, if it was not moving, or moving at a constant velocity. When will the acceleration be closest to 9.8 meters per second? Let's see. If M1 was really, 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 really light and M2 was really, really, really heavy, then it's going to fall like if I was dropping an object, which means it would be acceleration very close to gravity. So if M1 is tiny and M2 is large, could it ever accelerate faster than 9.8 meters per second squared? No. Unless maybe something was pulling it, if there was an extra force pushing it, maybe if we were on a different planet. So there are some ways that it could happen, but usually not in our classroom. If M1 had a mass of 3 kilograms and M2 had a mass of 2 kilograms, what's the acceleration of the system? Well, we did our analysis and we saw that acceleration is going to be equal to the sum of all forces, which in our case was FGM2 divided by mass 1 plus mass 2. Well, F equals ma, right? So the force of gravity on the mass is going to be the mass times the acceleration. Well, the acceleration to make the force is coming from gravity. Therefore, the force of gravity on M2 is going to be equal to mass 2 times gravity. In this case, my mass of number 2 is 2 kilograms, and we're just going to call gravity 10 for this problem, make the math a little bit easier. So 2 times 10 is equal to 20 newtons. So I know my sum of all forces is going to be 20 newtons. And mass 1 is 3, mass 2 is 2, so that gives me a total mass of 5 kilograms. Therefore, my acceleration is going to be 4 meters per second squared. Notice it's an acceleration. I need to have the units of meters per second squared. Okay, it's an object accelerating, and we go back to our old friends, the graphs. What would the following graphs look like for an accelerated motion of the Atwood's machine? Well, I know it's going to accelerate at 4 meters per second squared, but it's going to be constant acceleration. That's going to be a straight line. The velocity is going to increase at a constant rate, right? So the velocity versus time graph is going to look like that. And my position versus time graph, it's accelerating, so the slope cannot be constant. And my position versus time graph is going to be a quadratic relationship. Okay, that's it. I hope hopefully that helps, and I look forward to your learning. Please ask questions and do the check your understanding problems. Bye.